check whether, sir.
Hello.
Hello, sir. Hello, check whether, sir.
Let us start.
Okay, sir. You can start the session, sir.
Good morning to all. Am I audible, Dhanraj?
I can hear.
Yes, sir. It's audible, sir. It's audible.
Good morning to all. I, Dr. KVP Chakradhar, on behalf of Department of Mechanical Engineering, Vardhaman College of Engineering, is glad to introduce the honorable speaker for today's forenoon session, Dr. Ashok Udaygiri. Dr. Ashok Udaygiri is presently working as Associate Professor in the School of Physics in the prestigious University of Hyderabad, since 2006. He had completed his MSc and PhD degrees at University of Hyderabad and followed it by postdoctoral at Tata Institute of Fundamental Research, Mumbai, Rice University, and Raman Research Institute. He is one among the two teachers to receive Optical Society Association Senior Fellowship from Optical Society of America. He is life member of Indian Physics Association. His research areas include quantum optics, optical tweezer, complex fluids, laser cooling, microreology of complex systems, and shock propagation. He has published more than 50 research papers in reputed journals. Photography is his hobby. This is a very brief introduction for our erudite and distinguished speaker. Before I conclude, I thank the college management, HOD Department of Mechanical Engineering, organizers of the FDP, and each one of you for providing me this opportunity. Thank you. Thank you. Sir, I request our honorable speaker to take over the session. Ashok, sir.
Okay. Yeah. Thank you very much. Thanks to all the organizers and Professor Rao for making me part of this. I am assuming that most of the audience people are mainly from engineering background or computer science background. So I thought I would keep my talk to more on the introductory level of some of the technical aspects of quantum mechanics, which is necessary for quantum information. So if for some of you it sounds too basic level, you'll have to pardon me on that part. And perhaps maybe it's partly my fault that we should have discussed a little bit. So it would have been a nice if my talk was here and then it was followed by I listened to the previous speaker's talk, and some of the, at least I listened to some of the questions raised by some of the participants. Perhaps this will give some answers to some of those questions, and maybe it would have been better if I had preceded their talks, because I'm keeping it at a very fundamental level. So if some of you find it, again, let me repeat that statement, if some of you find it too base level, you'll have to forgive me on that part. But I hope that see, the main problem is that some of the things that physics people use, because most of us go through a full course on quantum mechanics, so some of the jargon especially, it's very obvious, so most of the times we don't even bother to explain what it is. But assuming that for people from other areas, I mean, the same thing will happen if I listen to an engineering talk, obviously. So I'm try to make you understand some of the basic concepts which you would need, and in retrospect, I'm sure you will realize that you will understand some of the things that the predecessors, especially Professor Bera and Professor Jairam Jaikumar, were talking about. So the basic idea is what I'm today giving is an oversimplified primer on quantum mechanics. I'm not going to get into details, and some of the things I'm even giving a little bit of a hand waving things, not a rigorous part of it, but it will help us understand and make sense of what most of us keep talking about. So we'll start with the classical physics. The whole idea is to build a mathematical framework of the real world, so that the mathematics mimics whatever is happening in the real world, and so we'll be able to both predict and understand uh, how nature is working. So essentially we are building a mathematical framework. The idea, and because of mathematics, the rules of mathematics are so rigorous that 2 plus 2 always has to be 4, provided I'm handling regular natural numbers, not some modular arithmetic or something. And so it kind of makes sense to see, especially when we get some non-mathematical result, we'll also throw it away as non-physical result. Okay, so the classical mechanics did a fairly good job of it. So the idea, to give you some examples from classical physics. So let us say I have a classical particle moving around. The typical jargon that physics will use is a classical particle moving in a force field. That means some force is acting on the particle, and so the particle is moving about, it's getting affected by this force field. And what you will need, all that we will need to represent the trajectory of the particle is x and x dot. X dot is dx by dt, which is the velocity of the particle. Or to be more correct, it is x and momentum, the position and momentum. Or if I'm doing in 3-dimensional, it is r and m r dot. Okay, so these two parameters are enough to tell me the complete story, past, present, and future of the classical particle. Okay, so now everything else is represented as some mathematics which will operate on these things, these two parameters, and change it. So for example, force changes x dot, and velocity changes x. Okay, so if I know this much, it's pretty much good enough to represent the whole of classical particle moving about it. Most of you have gone through a course in thermodynamics, and in thermodynamics we built something called an equation of state, which is a function of pressure, volume, and temperature. Okay, so now the entire thermodynamics is now represented as how pressure, volume, or temperature changes, or rather how pressure and volume follow it. And so you write the entire thermodynamics now becomes just a bit of a circus of making these parameters. Again, most of you have gone through circuit theory. All you need is a charge and the rate at which the charge is changing, which is nothing but current. Okay, so q and q dot. And notice something here. This is x and x dot, and this is q and q dot. So these two, not only the two parameters are very, very similar, with a little bit of a circus, you can even make the equations look somewhat similar, not exactly alike, but somewhat similar. So in 1900, a lot of people did a lot of work. Have people like Hamilton, Jacobi, Louis Lagrange, and all that. People try to do some kind of a unified picture of all of this. And we do teach part of it in the MSc course, as these things we call it as generalized coordinates, generalized position, and generalized momentum, and we go about this. So this gives you a brief overview of what is the spirit in which the mathematical model is built for as far as classical physics is concerned. Quantum mechanics, we change the whole rules of the game. Okay, now I'm going a little more than the normal quantum mechanics that has been given you introduction in high school about the Bohr theory or Planck's law and all that thing. I'm looking at what is present day mathematical framework we use, and this is not like the professor on Monday was talking about. This is not the only unique framework. There's nothing unique about it. Okay, this is one framework which we know very well represents quantum mechanics. Even in classical mechanics, there is no unique framework, and sometimes we change the framework to suit our requirements. Just to give you a simple example, I solve everything in XYZ coordinates. But then if I know that my system has some kind of a cylindrical symmetry, let us say I need to solve Maxwell's equations for light going through an optical fiber. Optical fiber has a cylindrical symmetry. It is same thing on around theta. So now I change all my Maxwell's equations. I rewrite in terms of cylindrical coordinates, r and theta and phi, and that gives me the biggest advantage because I don't have to solve for theta because I know it is the same for all the thetas. So I only need to solve for r, which is the distance from the center of the fiber, and z, which is the as it propagates, right? And if I have a spherical symmetric, I'll have to solve it in a complete spherical symmetry. And those of you who have done some amount of microwave, you are in trouble because the most of the microwave waveguides are square, so you have to solve it in XYZ. There is no, you cannot solve like an optical fiber. The kind of method you use to solve optical fiber does not fit for a square shaped waveguide. So therefore, so what we are telling is we change the mathematical framework where doing mathematics becomes easier. So in a similar fashion, this is one very successful framework which is given by Schrodinger and others. So here we represent the entire system by a wave function which is given here, which is psi of the, for a particle, let's say this is for an electron moving in a force field, and because for electron what is important are the positions and time, and so this is a function of variables x, y, z and t. And the probability of finding the system in a particular state, the state, if I ask xi, yi, zi, t, the exact position, that is given by mod square of this psi. Okay, now this methodology has both pros and advantages and disadvantages. The main unique characteristic of this thing is that this will give me probability of finding the particle at all points from here to infinity. So I can ask a question, what is the probability of finding the electron in this room, or what is the probability of finding it on the other side of the moon, or finding it at the edge of the universe? I'll still get an answer. The system will give me an answer, right? I mean, at the, and for all times from minus infinity to plus infinity, it will give me an answer. The same mathematics will give me an answer to tell me what is the probability. Maybe probability is very small, far away from, in this room it will be high, just outside the room it will be very low, but still it will give me an answer. I can still ask a question. What is the probability of finding this electron at the edge of the universe after some time? The disadvantage of this is that it will never give me a precise, I cannot ask a question like, where is the particle? I just, that question itself is invalid in the framework of quantum mechanics. I cannot ask a question like, was the electron here yesterday in this room? No, only I can ask is, what is the probability that electron was here yesterday? And that will give me an answer. The same, it may give you a finite probability yesterday in another room also, and that is where things become a little bit non-intuitive, where reality and what is the mathematical framework may look at the point of it look a little bit complicated, or rather incorrect. But then this methodology has been very, very successful. There's one example I can give you is this, that if I have a let's say I have a barrier. Example giving is, I go to the zoo, there is a tiger and there's a huge 15 feet wall built of it. The tiger can never jump out of the barrier unless it doesn't have that much of energy. If I build a barrier of about 6 feet or 7 feet, it can jump out. Tiger can jump 6-7 feet, but not beyond that. So if I have a 15 feet barrier, it won't come. So now if you ask a probability, what is the probability of finding the tiger just outside the barrier? It will be 0. But for an electron, if I build a potential barrier, it, under certain circumstances, it finds out that it can still come out of the barrier, even though it doesn't have enough energy to jump over the barrier. So this is called as a tunneling, And tunneling has not only been proven successful, and you have heard of something called a tunnel diode or a Schottky diode, where the tunneling effect is actually used, or even a scanning tunneling microscope where the tunneling characteristics actually used. So the Schrodinger picture, although has a problem of not giving me an exact answer as where is the particle, it has been really successful in solving most of the problems. In fact, especially in molecular physics, where people try to build the structure and the properties of a molecule looking at solutions of this psi for an electron in that molecule. And it turns out that most of the things predicted is correct. So we take this as one of the successful mathematical models and we keep using it. Although in class we teach this is the only of things. So this is what I told. One computes probability of finding the system at all points and at all times from infinity to infinity. Okay. Now the dynamics of this system, how psi evolves, is governed by this thing called the Schrodinger equation. This is simply telling me dou psi by dou t, how psi changes in time. And this h, this parameter, is termed as a Hamiltonian, and this represents all actions that drive the system. So now this is in the realm of mathematics, where I know an operator operating on a function will change the function. So my psi, the wave function, keeps changing on the operation of Hamiltonian. So an electron, just to give an example, an electron, I put an electric field or a magnetic field, a Lorentz force, or it could even be a proton looking at a different kind of force, or a mesons looking at subatomic particles looking at different forces. So all of them can be described by this. This is a very generic framework called the Schrodinger equation, and all that matters finally is what is the correct Hamiltonian which describes all the operations going on the side, and that will tell me how whatever system I'm looking at behaves. Okay, so I mean, just stop me or ask questions. I know it's difficult on the online mode how to get back on questions, but you can interrupt me at any point of time, no problem. Okay, now some of the Hamiltonians have something called a stationary state. That is, that state does not evolve in time. So this dou psi by dou t is not valid anymore, because psi does not change in time for those particular state, and this entire equation reduces to a slightly different form, where h operating on psi s standing for a stationary state will not disturb the stationary state, but it will give me a scalar. This h is an operator, this e is a number, a scalar quantity as we call it. Okay, and if I can write my h later on, you will see how I can write it in a matrix form. If I write everything in a matrix form, this e turns out to be the eigenvalue of these matrices. If I write it in an equation form, some of you may have heard of something called a Sturm-Liouville equation, which is this is just one form of a Sturm-Liouville equation. Okay, because my h also can eventually becomes like a differential equation. So this will be one form of Sturm-Liouville equation. So E at this case corresponds to energy of the system. So as you can notice, the one thing you have to notice here is this, that h on any other state psi, h operating on psi will change the nature of the psi, the form factor of the psi, because that's how psi evolves in time. But in this particular case, for a psi s, the operation of h acting on the psi s leaves it undisturbed. Okay, so this is an eigenstate in the matrix language. This will become the eigenstate of the thing. You can clearly see this is like a matrix eigenvalue equation in the matrix language. And so we, even when I write psi not as a matrix, we have a tendency to keep calling this as eigenstate and eigenfunction or an eigenvalue, but not completely correct. Mathematicians will kind of dislike us for doing it, but we know what it exactly means, so we continue using it. Okay, and so one of the important things we'll have to do is that this psi s being a stationary state is very specific to the Hamiltonian. If I change the Hamiltonian, I have one kind of a Hamiltonian, and psi s is an eigenstate for that Hamiltonian. If I change this Hamiltonian, psi s is not the eigenstate for the Hamiltonian. Okay, why? What is the meaning of that? It will become clear in the next slide. Why I'm insisting on you to looking at that thing. Now, this is the difference. This is the main difference between the classical physics and the quantum physics. The process of measurement is also represented by a measurement operator operating on a function. In most of the classical physics, operators only represent how the system changes. Okay, the measuring part is kind of taken out of it. It's kind of obvious. I know what is the voltage, I know what is the charge on a capacitor. Somehow, because the whole idea is that you're telling the process of measuring the charge in the capacitor is not going to disturb the capacitor. Fixing a multimeter into a system is not going to change the current flowing on the system. And of course, we do teach in the classroom theoretically that multimeter has infinite resistance. It doesn't add anything of its own. But if you are which is okay if you are working with 230 volts and 5 amps current, but if you are working in a circuit where you are looking at CMOS circuits with a few less than a few milliamps current, then even sticking a multimeter will create a lot of problem, right? So we know all in classical physics there are areas where measurement does disturb the system, but in the quantum mechanics we build it in the mathematical framework itself. So measurement has its own Hamiltonian operating on the function. Okay, so for everything, so obviously this is it has to work like your time independent Schrodinger equation. What I showed you, this just I forgot to mention it. This formalism is called as a time independent because there is no explicit time dependency here. Where this is the more general Schrodinger equation. So I keep at least telling my MSc students that whenever somebody asks for Schrodinger equation, normally people write this. This is not the correct way. This is the actual way, and then this is a subset of this. Okay, only in certain condition this reduces to this, otherwise this is the most generic thing. This is a time dependent Schrodinger equation. And so which essentially means that the measurement should turn out to be this form, because if I, let us say I have an operator which gives me what the value of x of the wave function. Okay, in fact that doesn't make sense the way I define my wave function itself. Wave function I define that it exists at all uh, points. So it doesn't really mean x gives me x measurement, although we use it sometimes very wrongly in that context. Basically what it tells me is that the x operator pulls out the probability of the psi at that point. Okay. Now here is the most important part. A particular wave function which is an eigenstate for the x operator is not the eigenstate for the p operator. P is the one which gives me the momentum. Okay, so now you see that the whatever has been told to you in your high school as the uncertainty principle, that x and p can never be determined very correctly, is now actually come built into my mathematics itself. Mathematics clearly says that if an x operator operates on a wave function, that gives me a value, x value. P operator operating on the same wave function will not behave in the same way. It's actually going to change this wave function, because the wave function, it's the nature of the wave function. The problem is with the wave function, not with the operator. A wave function which is an eigen function for x operator is not an eigen function for the p operator. There are a few special cases where it becomes an eigenstate for both x operator and p operator, then it doesn't change, but in general it always changes. So the Heisenberg uncertainty now is actually built into the system, and this is something which at some point now it becomes clear, where both Devjyoti Bera and Jaykumar Radhakrishnan were all talking about, where the system gets disturbed. Now system gets disturbed because psi changes. Okay, on making a measurement, because measurement is now also an operator operating on the system. Okay, so all of these operators for position, momentum, energy, angular momentum, etc., has a related operator, and operating that gives me a related parameter, provided now this was what I think Dr. Debjyoti or Jai Kumar was mentioning yesterday. I mean, most of the speaker mentioned to you is that if the system is not the eigenstate, then the Hamiltonian disturbs it. That's what here it means, right? Because my uh, I already told you the position operator and the momentum operator, they are not compatible because the eigenfunctions for these two are not same. So therefore, if I measure, if I make a measurement in the same basis set, that's what yesterday I think Dr. Debjyoti was talking about. If I make the measurement in the same basis set, it mathematically it means that my function is an eigenstate of the same operator. Therefore, it will not change the function itself. But if I try to measure it in a different operator for which it is not the eigenstate, I am going to disturb the system. And that, because that operator will change the sign. So that is where in afternoon's talk I'm going to talk about quantum cryptography, where this uh, parameter is extensively used. Okay, so and as you can see, Hamiltonian itself is an energy operator because that E eigenfunction corresponds to energy. So with respect to it gives me the energy of the stationary state. So this is one picture, one methodology of making the quantum mechanics. I'll just take a little brief here if somebody has a question, because I'm going to give a slightly different picture in the next slide. Okay, if somebody has a question, I'll go through, or oh no, well, let me see here again. Just let me hold on. Okay, before I go to second method. So this is the example. So I have an atom, I have an electron which has a Coulomb interaction with respect to this set of nuclei here, protons, and this will give me the there is a Coulomb force between the electron and the nuclei, and from there I calculate the potential, and I will rewrite my Hamiltonian operator. I'm sorry, I should have put on a P operator here and a potential operator here, and I calculate the potential. So as you can see here, my Hamiltonian P square by 2m, if you do a little bit of juggling, it's same as half mv square. Okay, and because this is m square v square, and therefore there's a half here, and then I divide by m. So this is half mv square, which is the kinetic energy of the electron, and this is the potential energy. So as you can clearly see, this is kinetic energy plus the potential energy. So the Hamiltonian is a total energy. Okay, but then that is as far as a classical Hamiltonian is concerned. But now I rewrite it as an operator operating on psi, and that will change certain things, and it will have a set of stationary states, and it so turns out that these stationary states are exactly same as what the Bohr orbitals that you have studied. Niels Bohr initially said simply that electron keeps going around, and then I'll calculate the energy of the each orbit and each orbital, and then I'll find out what is the difference between each orbital that corresponds to one photon. And when he did the calculation, it turned out to be exactly same as Balmer series, Lyman series that people had been seeing, the emission of hydrogen. So they knew that Bohr's idea was correct. So now again, the Schrodinger idea is also correct, because in the Schrodinger idea, we see that the stationary states in the operator picture also turn out to be same as the Bohr orbitals that we had already known from a semi-classical methodology of Bohr. Okay. So I'm presuming that nobody has a question at this point. So I'll go a little further. Now we go to another method, which is a slightly different method. So now all of this here, we constructed a function of the variables x, y, z, and t, and then we saw how that function evolved in time and space under different conditions. In the second method, we know that for a given Hamiltonian, I can construct a whole series of stationary states or eigenstates, and now instead of the function variables, we use the stationary states as the basis states. Okay, so and now this is I'll come to the why this is mathematically correct. Now the dynamics of the system is analyzed as it traverses along the basis states. Okay. Now this comes because okay, this is not something I'm telling that it happens. This is coming because of a theory of functions, and some of you have taken some. I don't know how much of. I'm sure even in the engineering courses there is some amount of theory of functions. Mathematics is taught because after all, the book we use, ARFCAN, is called as Mathematical Methods for Physicists and Engineers. So I'm sure most of you have gone through the same ARFCAN that we have studied. So the theory of functions says something here that I can represent any of the theory, any of the functions, any function can be used as a linear combination. Okay, let me put it this way. This turns out to be in the math. I'm not giving you the whole picture here of how the P as an operator looks like, but take it from me at this point. This turns out to be something like a d by dx kind of a solution. So it's P square, it's P operating twice. So it is d square by dx, differential operator operating twice on a system. So therefore this essentially becomes a second order differential equation operating on psi. And second order differential equation is a harmonic oscillator is the best example of a second order differential equation. And in harmonic oscillator waves and oscillations, they have taught you again and again, telling that there are normal modes, and any oscillation can be represented as a linear combination of all the normal modes. Okay, so something similar happens here, that when I take the stationary states of the system, I can represent any state as a linear combination of all the stationary state. I'll give you an example in the next slide, and that will become very clear what I'm talking about. Okay, so for instance, when I take the example of the hydrogen atom, which I already showed you, an atom, the stationary states of this equation represents all the allowed orbitals which Bohr gave, all the Bohr orbits, n equal to 1, n equal to 2, which you have studied in high school, turns out to be the stationary states of the Hamiltonian that I showed you earlier. Okay, so now I will tell that any the situation of the atom can be represented as how much it is in the ground state, how much is in the excited state, how much it's in the other state kind of thing. Okay. This is the same thing I told you. If Hamiltonian is in a matrix form, stationary states will be eigenstates. Okay. So any state of the system will now can be written as the psi of x, y, z and t I wrote can be written as a function of ci phi I, where all my phi I are basis states and these are the weightages. Okay, so it is C1 phi 1 plus C2 phi 2 plus C3 phi 3 etc. up to Cn phi n. If I have n basis states, I can have the that many stationary states. Okay, Ci is the weightage. And now this is again coming from theory of functions. This is not coming exclusively from mathematics. All the stationary states, as I told you, are like normal mode oscillator of a harmonic oscillator, and they are all orthogonal to each other. The orthonormalicity comes when you look at a function and look at what we call as the basis states. So if I integrate, because these are functions in x, y, z and t, and if I forget the time dependence, if I integrate over all x, y, z and x, y and z, this is the volume integral. Psi phi I and phi j star represents for the complex conjugate. If I take a system and someone else's complex conjugate, it gives me a Kronecker delta. That means that if phi I star will be 1 and phi j star for any other j will be 0. So these are orthogonal and normal. Therefore, these obey the rule normal. So therefore, this gives me an interesting thing. I'll take the total psi, which is a linear combination of all C1 phi 1, C2 phi 2, C3 phi 3, etc., multiplied by a phi I star, and then only one term remains, only the phi I term remains. Okay, if I multiply by phi 3, phi 1, phi 3 star will go to 0, integral phi 1, phi 2 star will go to 0, only phi 3 star will give me 1, therefore this integral value will be C3 mod square. Okay, we already told you that this is the probability of finding the system in state 3. So if I represent my total system phi psi as a linear combination of C1 phi 1 plus C2 phi 2 plus C3 phi 3, this is a mathematical way of getting what is the probability it is in the third state, what is the probability it is in the fourth state, what is the probability it's in the fifth state. So this mathematics for me becomes reasonably straightforward. Okay, and so this I'm going back here, so I have written it as a C1 phi 1 C2 phi 2 etc. Now mathematically I know how to extract one of the probabilities. As I told you, I cannot ask a question whether is it in the first state, is it in the second state, is it in the third state. That question itself is invalid. All the question that I ask is what is the probability of finding the atom in the first state, the second state, the third state, etc. And and each of these state will have its own energy. And and this is not, I'm giving you an example of an electron bound to an atom, but this can be used for anything else, even for an electron in a potential well. So for example, I trap an electron in a two potential barrier, like which is again like what your diode, you have seen your diode. There is that um, between the p-n junction there is a barrier in which the electron gets trapped. I can immediately find the force acting on the electron, and I can write a corresponding Hamiltonian, and then I'll get all the stationary state for it. Simple harmonic oscillator normally gives me a stationary states. And so at this point you don't have to worry about this, but at least now you're kind of getting a little bit familiar of the words that we keep using. Okay, so what is the meaning of those words? That was the whole idea for me for this talk. It would have been nice, as I said in the beginning, if this talk was the first talk, so that what the talks of yesterday and day before would have become a lot more clear, is what I felt. Anyway, I mean, of course, you will be the best judge of telling me. The main advantage of this method is this: the exact functional form of phi I now is not relevant. Okay, all I need to know is that I need to know what kind of stationary states are available. The functional form of the stationary states is also not relevant, and the dynamics now is seen as variation of weightages of Ci. Okay, how the values of Ci keep changing. Okay, and this gives me the other big advantage. This gives me is that this representant becomes very generic. Whether I'm looking at hydrogen atom, whether I'm looking at helium atom or lithium atom or potassium atom, there are some number changes because the weightages change differently. If I had to solve the Hamiltonian, actually in the first part I had given you the correct Schrodinger equation. The functional form for hydrogen atom is very different for functional form of helium atom, or of a rubidium atom, or a uranium atom. Now, with this way, the functional form does not matter. It's only the ground state, the first excited state, the second excited state, and so on and so forth. And I will start only looking at the weightages of it being in the first excited state. So which atom I am looking at almost becomes irrelevant. Or even whether it's an atom I'm looking at, or as I said, an electron, a free electron in a metal trapped in a particle, or as the free electron goes through a crystal, it's going to see bumpy, it's going to bump across all the ions sitting in the crystal. It doesn't matter. The moment I know that I can find out the eigenstates of the system, and then I can pretty much solve the equations, look more or less same, and that makes life a lot simpler for a theorist. But it also makes it a little more difficult for an experimentalist, because the theorist always gives in terms of numbers which doesn't make any sense to the experimentalist. Because a theorist will never tell you how much voltage how much current, how much energy actually you have to supply, he will simply say you apply equivalent energy. It's more like your cooking recipe, add salt to taste, whose taste is never put. Okay. Now, in 1928 or something like that, there was an English gentleman called Paul Dirac, P.A.M. Dirac, Paul Adrian Maurice Dirac, and he kind of brought in a little different notations, which makes a lazy physicist life even simpler because I don't have to write it. So what his notation was this. So I have an integral phi j star phi I d tau. This is a volume integral. He simply puts a bracket notation like this. Uh, and he calls it as a bracket, and he calls these two ends of the bracket as bra vector and ket vector. I'll tell you why the vector part comes in. And so he rewrites this entire notation like this. So I'm not written here. I'm sorry, I should have written here. So phi I bra vector, phi I ket vector will give me 1. Okay. These are normalized uh, vectors. So now we yesterday or day before somebody was asking why this vector. So now I'm telling you how this vector notation has come into picture. So you take all this. Have I written here? Okay. Okay, I'll come back to that. So I think you will understand this now, and uh, I should have written this as phi I as 1, no problem. So phi j acting on psi now, the bra vector phi j, this is equivalent to an integral phi j star psi d tau, and that gives me, as I showed you in my previous slide, cj mod square. Okay, because psi is now represented as expanded as in terms of phi up, phi 1, phi 2, phi 3, etc. So again, I go back to my atom. So quantized energy level, each quantized energy level now is represented by one stationary state psi, and it has infinite number of energy levels. So now I come to a standard notation which I'm sure people have been using in the talks, or at least in the further talks. If you end up calling a physicist, you'll see this notation. This essentially means a ket vector in the Dirac notation. And so I have all the energy levels, level 1, level 2, these are just labels I'm giving. Again, now as you can see, I'm really not bothered about the functional form, what is the exact functional form. So in fact, for a hydrogen atom, psi of x, psi of r actually will turn out to be something like e power minus r square by sigma square. It's a Gaussian function, and it doesn't matter. Okay, actually I should have shown you that picture. Anyway, it doesn't matter. Now, so the net wave function is now written in the Dirac notation in this format. Okay, so each of this 1, 2, 3, 4 represents the, normally the first one represents the ground state. This will be the first excited state of the atom if I'm talking of the atom, or whenever there are energy levels, and this will be the third one, the fourth one, etc. For an atom, what happens is that the probability, I mean, this is the physics part. The probability of finding the atom in the nth energy state is, thanks to a German physicist called Ludwig Boltzmann, this is equal to uh, this function. En is the energy of the state, and Kb, this Kb is the Boltzmann constant, T is the temperature in the Kelvin scale. Okay, so as you can see that room temperature, this is about 300 Kelvin. This Kb is a very small number, 10 power minus 27 or something like that. And if I put all these energy levels, this is a minus exponential of minus e by kbt. Therefore, this number will be very small, very large, and this number exponential of minus e by kbt will be very, very, very small, except for the state 1. So for the state 2 itself, at the room temperature, the answer will be almost 0, 10 power minus 30 or something like that. Therefore, probability of finding the atom in this state is very small. Probability of finding it in this state is even smaller. Probability of finding in this state is even smaller. and only when I feed some external energy like shine a light or hit it with an electron, that is what happens in a discharge lamp. The electrons collide with the atom and take it to excited state, and then it will come back to give me a fluorescence. Okay, so only in that case if it goes from here to here. If I have to make it go from here to here, it's even more energy is needed. Therefore, normally what I can do is I can neglect all these states. I can as well consider them as non-existent, and then I say the atom only goes back and forth between these two states. Therefore, I'll truncate this fellow. I'll truncate this fellow and say that my psi is only C11 plus C22. Okay, and because unless I force the atom to go here, it won't go. Okay, molecules are slightly different problem. There are too many close by energy levels, but for an atom this works very well. Therefore, I can neglect any of these things and I can write my state like this. So my psi is C11 plus C22. You have to forgive me a little bit. I'm kind of jumping between capital C's and small c's. I'm sorry for that. It's a mistake. It doesn't really, it's not too much of a mistake, but as long as you don't get confused. Okay, so this is my entire wave function now. This is a truncated wave function because the rest of it don't matter at all, because C3, C4, C5 will be very, very small. It will be almost zero. So now I can build a vector picture. Why I went to this, I can build a vector picture for any amount also, but this makes sense very clear. So now the state is represented by a vector. It's simply this vector, and the projection of this vector on the basis state 1 is C1. The projection of this vector on the basis state 2 is C2. So now you understood why the vector picture comes up. This is the energy level picture. This is my wave function, and this is a corresponding vector picture. If I consider 3 levels, I need a third dimension also. Okay.
Hello, sir.
So yeah, tell me please.
Yeah, I got it, sir. This vector format. I think it's
Vector
clear.
format. This is the question you were asking the other day.
Thank you, sir.
Why this?
Thank you.
Format? Yeah, good.
Yes, sir. Thank you, sir.
Okay. So now, if I have 3 basis states, if I have to represent a system with 3 basis states, I'll have a 3-dimensional vector space. And if I have to, this is difficult to visualize, but mathematically it's easy to represent. If I have n basis states, now I construct an n-dimensional vector space. Now my state is represented as a vector in the n-dimensional vector space. There's another important aspect of this picture. If you can see here, the length of this is C1 square plus C2 square, which is actually the total probability, right? C1 in this case. So therefore, the length of the vector is the total probability, and because the total probability is always 1, in the dynamics, the length of the vector never changes. So all that changes here is values of C1 and C2. So if the vector comes here, C2 has become different, C1 has become different. So all I need to know now, my entire physics now is reduced to searching how, understanding how C1 changes and C2 changes. So if I have a 3-dimensional system, C1, C2, C3, how they change. If I have an n-dimensional system, I'll have to keep on looking for how C1 changes, C2 changes, C3 changes, C4 changes, up to Cn, knowing very well that the mod square is always 0, mod square is always 1, therefore the vector length never changes. So the vector is actually rotating in the vector space. Okay, so that is the physical picture. So sometimes we are kind of, if you are not very familiar, we make a statement like, oh, the vector is rotating, and then you'll start of understanding why we are talking about this. Okay. Right, good. So now for any given state, we have a finite number of basis vectors. If sometimes, okay, there is a mathematics allows you to have an infinite number of basis vectors, and you can build an infinite vector space. It's very difficult to visualize for us anything more than 3D because we are familiar with 3D, but mathematically we can do, and mathematics people are extremely what do you call it? They're handy, and some of them even talk of a continuous vector basis kind of a thing. I mean, even it's not even. Now you also understood the orthonormality, because here you have done it in high school. I vector and the j vector, the unit vectors are orthonormal to each other. So now that's straight away coming on to me right away, that the vector 1 and vector 2 have to be orthonormal to each other. Okay, in a 3D, all the three vectors are orthonormal. In an n-dimensional vector space, they're all orthonormal to each other, and that's a bit difficult to imagine. The angles are 90 degrees, but still they're orthonormal. Okay, so don't get into that thing. That's too complicated. But angles are 90 degrees. So how do I have a 4-dimensional, 5-dimensional vector space? Okay, but mathematicians don't really worry. At some point, mathematicians stop thinking of the real stuff, so they can build really juggling a lot of things. Okay, so now it's just I'm repeating the same thing what I've said. The Hamiltonian will now act on the vector and modify the weightage as Ci. So it will all become the same thing I said, mod Ci square is equal to 1. The vector is always normalized. So now that becomes very clear. Now I'll go to the representation which Dr. Devjyoti was using, it very familiar yesterday. So I'll rewrite this, my whole Hamiltonian equation. I'm not neglecting the presence of it, but I find there's no need to represent state 1 and state 2 because I've already denoted that the first row is represents state 1 and the second row represents state 2. If I have third row, fourth row, fifth row, this is a convention, and there is no nobody says I cannot write 2 here, 1 here. I cannot write 1, 2, 3, 4, 5 like that. I can go up or I have to go down. There is nothing fixed as long as in your entire mathematics you stick to one notation. That's all. As long as you don't mix up your notations, everything is fine. Okay. So now I wrote the vector. Forgetting the I'm not denoting the basis sets. I'm writing like this. So now my Hamiltonian can now be written in a matrix form. So you realize what I wrote. Earlier I wrote dou by dou t of psi is equal to h psi. I have neglected the IH cross here, IH bar. For those of you who have a problem with it, physics people usually write, I don't know how you write your Planck thing is h nu or h bar nu. H bar is h by 2 pi, sometimes called as a Dirac constant. So the Planck energy is h into nu. Sometimes, most of the times when students come into physics, we write the Dirac way, which is h bar into omega, the angular frequency. Okay, and most of the times we are more familiar with h bar. Then I have taken the IH bar, which was here in the earlier equation, into this. So now I have rewritten equation in this way. Now you also understood why I kept calling it as eigenstate and eigenfunction, because the moment I write it in a matrix form, I'm going to get eigen values and eigenfunctions. And one thing which has been told to you and may be forgotten is that if I diagonalize this matrix, on the diagonal I'll have zeros here and I'll have zeros here and I'll only have eigenvalues here. Okay, so I will come to that. I'll come back to this after showing you the next slide. I'll come back to this, but let me see again now. As I told you, this is a very generic model which will fit several different systems. So it can be two energy levels of an atom, spin up and spin down. Those who have been taught of spin and doing some amount of semiconductor physics, put some quantum mechanics showed into you talking about the spin. The spin is a bit of a misunderstood thing. Initially, they thought that the whole electron was spinning around itself. Today, I should say we have no idea what it does. Okay, but we have a mathematical quantity which gives me the same numbers. And if I take an electron with a spin down and put an external magnetic field, it will align following downwards against the magnetic field. A spin up will align itself along the magnetic field. So we continue to call it a spin up and spin down. And so a molecule or an electron in a molecule, etc. I'll have a spin up system, spin down system, and people have been using. I don't know the other TIFR person who is using quantum dots and spin systems for quantum computation. So someone else will probably talk to you about this, that I have a Josephson junction and then I'll have a current going in this direction, clockwise in this direction and anti-clockwise in that direction. If I give an RF field, the current will jump in the superconducting ring from an anti-clockwise to a clockwise. And again, I have exactly the same formalism for this. What is the probability that it's going clockwise? What is the probability that it's going anti-clockwise? And what makes it change these probabilities? Okay. Or I can have two polarization states of light. How much is vertical component, how much is horizontal component, and what makes it go from a vertical component to horizontal component. Or I can have a left circular polarized light, right circular polarized light. So everybody is using the same mathematics, and that is why you have in the quantum computation business, you have at least a dozen different type of people who are looking at different type of physical systems, and we all talk the same mathematics at the end of it. Okay, and we understand each other unless somebody is talking of an experimental system, because experimental system becomes very different, and there are some specific things one has to be very careful between two energy levels of atom and spin up and spin down. For example, for an energy level of atom, the excited state is a short-lived state. Okay, if I put the atom in the excited state, after a few nanoseconds it will come back to ground state. Whereas if I take a spin up and spin down, that for several microseconds it will stay there. There's nothing like that. So those things I'll have to build into the Hamiltonian when I look at the time dynamics, and no such thing happens with respect to polarization states of light. So those differences exist, but but all of them can be incorporated into my Hamiltonian, and the overall dynamics, the equation looks almost identical. I should say almost identical, and therefore we can easily jump from one system to other system without really bothering about what system I'm using. So I come back to say that the stationary state means that dou by dou t, or a Hamiltonian acting on C1 and C2, will give me the eigenstates. So look at this. Hamiltonian acting on C1 should give me some energy into C1. Hamiltonian acting on C2 should give me some energy into C2, which essentially means that for a stationary system, this should be 0 and this should be 0. So H11 acting on C1 will give me E1 C1. These are operators again, remember. H22 acting on C2 will give me E2 C2. Okay, so this represents the eigenstates of the energy, the diagonal terms, and this represents the coupling terms, because look at this one, it's H11 C1 plus H12 C2 is how C1 evolves. So d by dt of C1 is H11 C1 plus H12 C2. So how C1 depends on C2 is determined by this fellow. How similarly d by dt of C2 is H21 C1 in plus H22 into C2. So H21 C1, that determines how evolution of C2 depends on C1. Okay, so this becomes the what we sometimes kind of loosely call it as a coupling. These are the diagonal terms, which are the eigenstate terms. So that this also makes sense with your matrix formalism, where I told you already that eigenstates, if I can turn this Hamiltonian into matrix, this matrix into an equivalent matrix where only the diagonal terms exist, and that will be the eigenstates of it. But I cannot turn, if this is a time evolving system, if I know that there's a particular factor for which it doesn't evolve in time, I can do it that way, right? So that is a diagonalized Hamiltonian. So now the matrix form also becomes very clear for you. I already made you familiar with the vector form, the matrix form. So I am going from a functional form psi of x, y, z, t to a vector form to a matrix form, and that makes now all the talks kind of very clear now from now on. Okay, this is what I already told you. I'm just putting it in words so that I'll remember telling it to you. I'll go a little more on the two-level atom. I'm assuming my time is still 12 o'clock, right? Yeah. So the beginning, Ms. Dhanraja, Professor Rao, tell me if I'm kind of overshooting my time. In the beginning, already I told you the atom is in the ground state. So I'll go a little more on the two-level atom. So C1 is equal to 1 and C2 equal to 0. Okay, because the ground state, it's already there. Ground state probability is 1 and the excited state probability is 2. So now I rewrite the vector like this. Okay, this is not the same thing Debjyoti Bera was writing yesterday. I'll come back to that in a little later. Okay, and therefore in the excited state, so this is the ground state. C1 is 1, C2 is 0. The excited state, sorry, I made a mistake here. I'm very sorry about it. This should be 0 and 1. Okay, I'm really sorry about that. So it would be a flipped system. 0 and 1 is the excited state. Okay, so let me just go back here a little bit for a moment. A little bit. Okay, let's look at this. C1 is 1. Excuse me for a moment. Just for a moment. Hello, I'm in a meeting. I'll talk later. Okay, so C1 is 1, C2 is 0. That means this entire vector is here. So when I go to excited state, C1 is 0 and C2 is 1, so the vector goes here. So vector has literally rotated from here to here along this way. It's completely rotated from here to here like that. Okay, so the transformation of the Hamiltonian, taking it from ground state to excited state, can be seen as a rotation and that comes to something very important I'm going to talk about. Okay, so any other values here, which means that the atom is in a superposition of ground state and the excited state. Okay, which means that there is a probability, some probability of finding it in the ground state. There is some probability of finding it in the excited state. It's not definitely 1 and 0. 0 means I don't find it in the excited state. So I can have some finite probability. This is something not quite imaginable in a classical system. How can I be both at, let us say I'm on the ground floor of my building and also on the first floor of the building. I find some probability of finding me in the ground floor of the building. Sometimes it happens. Okay, the guy could be in, there's a 70% chance that the professor is in his office in the ground floor or is in his lab in the first floor or in a class in the first floor. Okay, 20% chance that he is there, 80% chance that he is ground floor. These things can happen. Okay, but for a quantum mechanical system, it's very peculiar, and you can reach a state where these are, remember, as Professor Jaikumar was telling, these are probability amplitudes. These are not probabilities themselves. Only when I square it, I get the probability. Okay, that's why they are called probability amplitudes. So the exact 50% probability will make it as square root of 2 and square root of 2. Okay, that's what I'm representing here. Okay, so C1 is equal to C2 is equal to 1 over square root of 2. Okay, so that C1 mod square is equal to C2 mod square, which is equal to half. So the probability of finding it in the ground state is half. Probability of finding it in the excited state is also a half. So the probability of finding it can both be in ground state and the excited state. Okay, this is not a bit of indeterministic. It should not be confused. This is a bit peculiarity of a quantum mechanical system. The classical system is indetermination. That is, I don't know if the professor in the ground office in the first floor or in the class in the first floor or office in the ground floor. But that's why I write a probability. But somehow in an atom, it turns out that it can really be in both ground state and the excited state more or less simultaneously. Okay, this is again a shortfall of the probabilistic description of the quantum mechanics. Okay, I can never get a definite answer for this. So these are called the superposition states. Initially, there is still a bit of debate of how much real is this superposition state, but I'll come to that superposition state in a way. Now I'm going one more mapping, which sometimes look as confusing to this one, but this is what Dr. Debjyoti Bera was talking about. So I have two bits, 0 and 1. So now I map it to ground state of the atom. I'm sorry, please. Just hold on for a second. Hello. Good morning. I'm in a meeting. I'm on an online meeting. I will talk to you a little later. Okay, maybe half an hour later. Yeah. Okay, sure. Yeah. Right. I'm sorry, there was somebody who needed my attention immediately. Anyway, so the bit 0 gets mapped to this vector now, which is the ground state of the atom. Bit 1 get maps to the excited state of the atom. Okay, or in case if I'm having a Josephson junction, clockwise and anti-clockwise. If I'm having a spin up and spin down and spin up. And this is again not unique. If you can say no, I don't like 0 going to ground state and 1 going to excited state, I will change it 0 to excited state and 1 to ground state. No problem, you can have it as long as you consistently stick to the same mapping throughout. It's fine, but stick to a mapping. That's the whole idea. So now I can go from atom. That's what somebody was talking of, a quantum register. So now you have most of you have used registers, and you are telling me that 0 volt is bit 0, 5 volt is bit 1. So now I am telling atom in ground state is bit 0, atom in excited state is bit 1, and the mapping for the quantum mechanical vector will become this. Okay, and of course a combination of 0 and 1 also I can write another vector, but that's not what we are talking about. Okay, so the superposition state, now this is the problem. Now I'm telling you, even with the mapping, so this is bit 0, this is bit 1, so my system is half probability is in bit 0, half probability is bit 1, and therefore my atomic level superposition is 1 and 1, and which maps to your qubit superposition. 0 q means 0 qubit and 1 qubit. So this is how my this is a mathematical representation of it, and this is the representation, this is a physical representation of it. Okay, so any system I'm getting now, this is my physical representation for a information being both at bit 0 and bit 1. Okay, so now as long as you don't get confused between this and this and this, it is fine. Okay, what Dr. Devjyoti was talking more of this representation yesterday morning. Okay. Okay, so why we went through all this circus is this. My nice humble switch. Okay, and this switch they have already written as 0 and 1. So this is off state, this is on state. The switch is always put in such a way that it can either be off or it can be on. A quantum mechanical switch is like a switch with the spring gone bad. Don't know whether it's on. It's not that you don't know whether it's on or off. It can simultaneously be on and off. You cannot go between both. A classical switch can either be off or on. I'm looking at a good, well-behaved switch, not the switch which has gone bad. It can either be off or on, but not both. Whereas a quantum mechanical switch can be prepared in a superposition of both off state and on state simultaneously. Okay, it exists simultaneously in both on and off state. And what it physically means with respect to this is confusing. Don't even try that part. Just look at it mathematically and say it can be so. Now this is where quantum computation comes into picture. So now quantum computation gets mapped. All your computational operations that you have learned, if you have gone through a course of theoretical computational physics and computational science, you write a whole set in terms of an algorithmic methodology without realizing what exactly the algorithm means. Now also starts getting mapped onto a certain types of Hamiltonians which acts on a quantum vector. Okay. And so all your NOT gate, NOR gate, AND gate, all the gates get mapped onto this. And so that is what yesterday, I don't remember who was talking about it. Maybe Dr. Bera was talking about it. Professor Jaikumar was also talking about it in a little bit, that a simple NOT operation, we know that we have done our digital electronics. So a NOT operation will take 0 to 1 and 1 to 0. But what happens to a NOT operation acting on this? The NOT operation acting on this will take the 0 to 1 and 1 to 0. So it is simultaneously going to flip these two. So it will become C0 1 and C1 1, or you can put it this way also. And if you recollect the vector picture I wrote, it essentially makes the vector rotate by a 90 degrees to another state. So that's what your operation. So now I can rewrite operations in terms of rotational matrix, and somewhere in your um, for your BTech course, somewhere if you scratch your brains a bit, you will recollect that you had written how to rotate a vector in the vector space. You had that sine theta, cos theta matrices. Now I can exactly write the same matrices here, except that my theta will not be angle. It will be something else which is related to some other parameter. I can still use it as an angle which will rotate. So the not operating on a qubit will take, this is what I call as a qubit now, because this is a quantum bit now. Okay, it's not the same your classical fellow. And so now the qubit goes from here to here. I've completely rotated. 0 has become 1, 1 has become 0. Okay. So again, not to be confused, just because there are two parts here, this is still a single qubit. I've taken a single atom and prepared, or a single Josephson junction, or a single spin system, and then prepared the system into it's still a one register. It's still a single register. Okay. Now, so the not operating is a single bit operation. It operates on a single register. A Hadamard that Dr. Debjyoti was talking about was also acts on a single register. It takes a system which is in the state 0 and prepares it on a 0 plus 1. Was it Professor Jaikumar talking about it, or was it Debjyoti? I'm not sure, but anyway, I'm sorry, I messed up some notations here. This is supposed to have been R angle, not this. So it takes from 0 to 0 plus 1 and 1 to a 0 minus 1 state. That's the Hadamard operation. This operation becomes clear if you write it in the matrix form. Go back to this format. Go back to this format, and you write here as 0 1 for one of the states, or 1 0 as for the other of the states, and then you look what this operation is, and it will immediately come to you there is a minus sign in one of this, so it will become if this is 0, it will become 1 plus 0 plus 1 or 0 minus 1, depending on what the operation is still same. The Hadamard operation, the matrix for this is still the same. It's not, these two operations are not different in the matrix form. And I think that's an exercise you can do in the break, and then you will realize that this, what was told to you yesterday, becomes very, very straightforward. Okay, Hadamard is not a 2-qubit operation. It's still taking a single qubit. It's one register. Whereas the control NOT gate consists of two registers. Now I have two registers, both of them can be in its own set of zeros and ones. And what this does, one of them is called a logic bit, the other is called a control bit. I'm explaining this because yesterday and day before, all the speakers use this control NOT, and left, right, and center, and some of you, at least some of you, may be worrying what exactly it is. So I'm trying to, they didn't explain to you, I'm telling you. So I have two registers. One of them is a logic register, other fellow is a control register. This is somewhat equivalent to what you have done in digital electronics. You have a S1 and S2, and then what happens to bits, your controlled adder, controlled subtractor and all. One of them is always a control thing. So what happens to logic bit depends here. It's one logic bit and one control bit. What happens to logic bit depends on the state of the control bit. It's the same thing as your controlled adder that you have built. Your controlled adder, it adds if the control bit is 0, it subtracts if control bit is 1, or vice versa. Something similar happens here. If control bit is 0, operation does nothing to the logic bit. If control bit is 1, the operation changes. It becomes a NOT operation to the control bit. I have not specified whether the control bit is in a single state or is in a superposition of both states. It doesn't matter. This is a NOT operation. I mean, the NOT operation flips it. But whether the NOT operation works or it does not work depends on what is the control bit. The control bit controls whether the NOT operation happens or not. And why we so much talked of a control NOT operation is this. Like in digital electronics, you have been told and you have been made to do, you have been told that AND, NAND and XOR, or some of them are universal gates, which means that any operation I can represent it as a series of NAND gates. In a similar fashion, the quantum computational operations can be represented in terms of a control NOT. Control NOT becomes a universal gate. So any quantum computation algorithms, somebody else is going to talk to you about quantum computation algorithms. I'm not even that good an expert on it, and I'm not going to talk about it, like Ashore's algorithm, Grover's algorithm, search algorithm, etc. And yesterday some of them were also writing a circuit diagram picture of it. And it turns out that a Hadamard operation and a control NOT operation is good enough to represent any of those. Of course, it becomes more and more complicated as I can go, but in fact, it's not just control NOT. There are some variations of control NOT, like your controlled adder. You have a controlled phase gate and some other controlled gate, things like that. And a controlled gate on a single operation and a Hadamard operation is good enough to describe any of the quantum computational algorithms, and that is why most of us stick to this. And some of us who are trying to work on how to represent or how to make a control gate, we just say, okay, with this particular system I can do a control gate. With a pair of Josephson junctions I can do a control gate, and to a large extent I feel very happy that I have achieved something. Okay, I have not still built the quantum computer. the hardware part of quantum computer as of today, I should say, is more or less still in the form of the early transistors, the big transistors that Shockley and Bardeen and Brattain were building. Not the kind of, it takes some more years before we can hit the equivalent of the VLSI stage, but till then we are working on it. We are really struggling onto it. A little bit extra additional thing which perhaps this is because a lot of things get misrepresented in the public press or a general media. So this is what I want to tell you again, is this, that on the hardware side, people are trying to build quantum gates, again controlled NOT gates and the Hadamard gates, and it has not been very easy for a simple reason that I'm handling systems at the quantum level, because I do need a superposition, and most of the quantum levels are quantum states are very, very fragile. That means that they don't stay in the state for a long time. They interact with the surroundings. It has not been very easy. The technologies exist, but it's still very difficult to address a single atom. I mean, the VLSI people, you have done a remarkable progress. Like you put a 10 million addresses on a little 1 millimeter by 1 millimeter chip, and you can exactly address each single register and tell me what is in the register without meddling with the content of the register. Now that yet has not happened in the quantum mechanical system. We are not able to yet take 10,000 atoms and address one atom of it, or 10,000 quantum dots and address one quantum dot, 10,000 Josephson junction. We have not reached the state, but we are making considerable progress going on that state. Someday I'm sure we'll be able to do it. I mean, the progress has been pretty good. People have been able to do a lot of things, and someday the progress will come. But at the same time, there is a set of other group who are building up algorithms like a Grover algorithm and Shor's algorithm, and without having an exact quantum computer, they are able to show you algorithmically that if I have a superposition state like this, there are certain problems. Somebody yesterday again was talking about solving the problems, etc. A certain problems can be solved in a lesser computational steps. Okay, it's I mean, they have a tendency to tell you I can speed it, I can speed up the operations, I can solve it very fast. And even in the real quantum computer, IBM and the Japanese group Riken and all have now, they have put two systems. One is a simulator, that is, it's a classical which is behaving as though it's a quantum computer. That means they have built up operations, the NOT gates, control NOT gates, etc., in such a way that they have added some amount of pseudo randomness and all that stuff. So for an outsider, it behaves almost like a quantum computer. Okay, it does the same organization, of course, and of course it's not really fast because it's not doing a true quantum computation. They have built a true quantum computer. There is a company called D-Wave which claims it's been doing a true quantum computer. Scientists are a bit skeptical because a lot of parameters have not been made public. It's still a bit secret inside, and people are trying to see if I can write an algorithm which will tell me whether it's really a quantum system or something which is mimicking a quantum system. Someday we will be able to do that also. And as of now, the thing which the other person of Monday afternoon, I'm forgetting his name, Professor Rene, was talking about, is partly looking at how the simulator, a quantum computer simulator, and there are two things which you should not get confused. One is that I can simulate a real system on a quantum computer. That is a different thing. I can simulate a quantum gas on a quantum computer, or I'm simulating a quantum computer itself on a classical computer. Be a bit careful of exactly what people are talking about. Sometimes one can easily get confused with each other. And so as of now, the quantum gates that we are building are not much faster or not even as fast as your classical NAND gates and whatever gates that you've been building. Okay, so as of today, a simple chip that sits in your Android mobile can do a much faster computation than what the IBM's quantum computer can do if you are taking the absolute speed. However, there are certain algorithms which cannot be easily solved on a normal computer. I need a true quantum computer to solve that, and when that happens, we'll be able to solve it in lesser number of computational steps. That is very, very important. When they say fast, it means not really fast, it means a lesser number of computational steps, and that makes a huge difference when I'm solving big problems. Okay, even a normal regular computer which otherwise would easily add two numbers would falter when I'm trying to do a prime factorization of a 128 bit. Okay, so I hope I have okay, I'll go for the one last slide. This is something that some of them may use. Two slides actually. So there's a thing called density matrix which quantum mechanics people were using it, and this is a funny product of psi. If I write the psi on this side, I'll get a psi what we call as an inner product, and that gets normalized to 1. This is not 1. Okay, so if you look at it, if I write psi like this, so now you have to look at what is called, this is called as outer product, and that was the inner product. And if you try to get this, you have to write the ket vectors 1 and 2, and then you can work it out, and then you will find that I'll get a ket vector 1 and 2 which is something funny, and ket vector 1 and 1 which is not 1, and then I can write it in the matrix form, and you will find that that's why it's called as a density matrix. So it's called it will turn out to be C1 C1 star, C1 C2 star, C1 star C2 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 star. And as you can clearly see, C1 mod square was probability of finding it in the state 1, C2 mod square was probability of finding it in the state 2. So these two are the probabilities of finding it in state 1 and state 2 respectively. These two tell me how C1 is related to C2. Okay, that means, so this is the point here. If I look at this picture, this will only tell me what is the probability of finding it in state 1, what is the probability of finding in state 2, but there's no relationship between state 1 and state 2. Whereas here I'm also telling you the relationship between state 1 and state 2. So this gives me more detailed picture. It makes mathematics a little more problem. Instead of 2 quantities, I'm digging with 4 quantities. Okay. But somebody will in the future will start talking of density matrices, but now I know, yeah, I have already defined the density matrix, and so you know exactly what they are talking about. This is the last slide I have. This is again, I'm not sure, people will describe to you a slightly different form of it. This is your thermodynamics. Entropy has always been told you as a measure of disorder in your thermodynamics, but then Boltzmann and Gibbs gave a slightly alternative explanation where if I have a set of energy levels and the atom can occupy each of the energy levels, and the probability of occupation of each of the energy levels is given by pi, then pi log pi gives me a kind of normalized probability for an occupation of each of the level, and then if I take a sum over all of it and multiply by Boltzmann constant, I'll get the entropy. I'll get the same entropy that thermodynamics has defined for you. Okay, this is a microscopic description of the thermodynamic entropy that you have been taught, thanks to Boltzmann. And again, it will tell you, now you will see why the disorder comes in a slightly different way. If all the atoms are in a single level, then rest of the probabilities of 0, so this will be a small number. So your S will be a very small number, almost close to 0. It's an ordered state. All the atoms are in one energy level is, or the probability of finding the atom in one energy level is very high, entropy is very low. But if I can allow the atom to occupy many energy levels, this number becomes very large, so your entropy becomes larger. So the disorder is still coming into it. In somewhere in 1980 or 1970 or something, Shannon gave a mathematical theory of information where he built something very similar, where the probability of finding each information is given again in this, and because it looks so much similar to this fellow, he called it as a entropy. Sometimes we call it as a Shannon entropy. And so if I take two registers, if I take a single register, it can equally be in, I'm talking of classical mechanics, digital electronics, it can equally be in 0 or 1 with a 50-50 probability. So you can add the whole thing and get a entropy for it. If I have more registers, you will get a different entropy for it, and that represents essentially how many different amount of information I can have. The more more types of informations you can have, your entropy keeps increasing. Okay, that also becomes like an uncertainty. If I mix up all the information, the more registers I can have, the more messed up my information can be. If I have only one single register, I cannot mess up the information. It can be either in 0 or 1. But if I have more registers, I have many permutations and combination of these registers. So my if I drop your USB key in water, you can really have a messed up information. Okay, that is what is a higher entropy. Because I talked to you about density matrix, I can also decide a von Neumann entropy. It's the same von Neumann who gave your computer architecture, but he was also doing a lot about in quantum mechanics. He gave this as a reformulation of the Boltzmann entropy, which is meant for physical system. TR stands for trace. Trace, you know, in the matrix language is the summation of all the diagonal elements. So if I write row in a matrix format, if I take row log row, and ln stands for logarithmic to base e, natural logarithm, and if I take a trace, I'll also get entropy. So I have explained to you this because in the information theory context and computational quantum computers, quantum information, people could be using all of this. So I will stop at this point. I don't short my time. If there are questions, I could answer. And in the afternoon session, I'll be talking about quantum cryptography, not quantum information. So I've given you a bit overview of quantum information. So thank you very much.
Yes, sir. Thank you, sir. I have a question.
Yeah, please.
So now, in almost all computer science related research on quantum computing, it may be
Huh.
as an accelerator, or it may be machine learning or artificial intelligence.
Right.
They refer for the results always the simulator or the real quantum computers supported by the IBM.
Yeah. Yes.
To
Yes.
what extent we can say that it is correct, and what is your comment on that, sir? If anything, if
Uh,
like, which is, if my question is relevant.
question is relevant, but unfortunately, I don't have the answer because I myself have not really looked into it, and I've also talked to some people who are using it, and they gave me a kind of a very shrug their shoulders and say, "Look, we have not come to a stage where I have defined a problem." I mean, this is something again to give you an analogy, to give you a very much analogy, like you go back to your initial days of artificial intelligence, where they said that I don't know if I know the other side is a intelligent person or a computer, right? That your this person's I'm not getting his name, the guy who taught theoretical quantum computer science. So unless and until you formulate a question, such a question where a machine cannot answer, only a human being can answer, then you know whether the other side is a machine or a human being. In a similar fashion, till now, the scientists have not come up with a problem where only a true quantum computer will give me the correct answer, a simulator will not give me the correct answer. Apparently, they have not come up with such a system yet, because the quantum simulators, as of now, have been doing um, almost what a quantum computer would do.
Yes, sir.
Okay, but it'll do a bit more circus to do it than a true quantum computer would do, because I have to really for everything I'll have to have two registers, and then I'll have to play with it, kind of thing. I'm actually using more registers in a simulator than even for a classical computation to make you make it look like a quantum computer to you.
Yes.
For every bit I'm using two registers.
Yes.
Okay, so to fool you. So I'm actually using more resources, but this is a good exercise to learn how a quantum computer would really behave from the user end. Okay, so it's a joint thing. Things will evolve both ways.
Yes. Got it, sir. Thank you, sir.
Yeah, right. So anyone else? Any other thing? The hardware side, we have really not made much progress. I don't know how many bits the IBM's true quantum computer is using. I've not looked into it, but it's really not. I'm having a 128-bit system, a 64-bit system on your real stuff. Every register is a 64-bit, and I have so many registers even on my mobile computer. So mobile phone. I have not that reached that stage in a quantum computer. Nobody has reached. I think 8-bit or 12-bit or 16-bit is what they are talking about. It's not 16-bit several registers. It's just one register that's been handled. But soon improvement will come. Very soon. Okay.
So any questions from the participants?
Comments? comments are also welcome, whether you found it too basic, whether you found it relevant. Yeah, it was good, but not relevant to whatever we are talking about. Even that is good, because that will help me and your organizers. Your organizers will know next time whether they should call me or or they should tell me, no, don't talk about this, talk about something else.
Yes, the theoretical evolution is good, sir. Whatever your content you said today.
Yeah,
Uh,
right.
one my basic question, it is answered like I have a that vector representation of the quantum system state.
Right, right.
To get that, I think this is very essential. This theoretical all issues. It's very good. Thank you, sir.
Yeah. Okay, you're welcome. You're welcome. I mean, I know it because in a 2 semester quantum mechanics, we go take the student through the whole of this. So physics students will easily know it, and probably all your people like Debjyoti Behra would have sat through one quantum mechanics course before getting to it. So they would be familiar. So I know where the problems are. That's why I try to give it to you. So I'm sure retrospective, you will also understand what both Jai Kumar was talking about and what Dev Jyoti was talking about and Rene was talking about.
Yeah. Any questions from the participants? Participants can unmute the mic and then you can ask the question.
Okay, looks like they don't have. So when are we coming again for the afternoon session? What time?
Sir, at 2:30 p.m. sir.
2:30 p.m. Fantastic. So
Yeah.
So good. Afternoon, I'll be talking about explaining quantum cryptography, because that's been a bit again misunderstood and misrepresented. So let me make that clear. It's not computation, but it's still part of the quantum information, the whole quantum information universe. So let me talk about that. Okay. So
Yes, sir. Sir,
okay.
on behalf of all the participants, I would like to thank Ashok sir for his lecture on quantum mechanics.
Okay.
Thank you, sir. Thank you very
You're
much.
welcome. You're welcome. Thank you. You're welcome. Very warm welcome. It was a pleasure being part of this course.
Thank you, sir. Thank you very much.
Thank you, Professor.
Okay.
Thank you so much.
Okay, yeah, thank you. Thanks a lot for making me part of this. So we'll come back again at 2:30. So I'm logging out.
Yes, sir. Yes, sir.
Right.
So all the participants, that's the end of the morning session. And again, we will meet at 2:30 p.m. Yeah. Thank you.